My name is Peyton Holston, and this is my presentation for Physics 2211, Lab 4, Oscillations. So the goal of this experiment is essentially to compare and analyze the predicted and observed motion of a spring with an attached mass to a fixed point, and analyze the energy changes or the lack thereof throughout the movement of the spring in both the observed and predicted models. Some of the pertinent equations that we'll be using throughout this lab is, of course, the usual calculating net force, which we know will be consisting of the force of gravity and the force of the spring acting on the mass, using the velocity and position update equations to, of course, calculate final and velocity and final position. The new equations we'll be adding are the work energy principle equations. Here you can see there is delta E, delta U, and delta US, specifically for the spring. Here we have Hooke's law, which we'll use to calculate the spring constant for this particular experiment. So this is just a breakdown of how to calculate the spring constant and the relaxed length, which we'll need for this experiment. Essentially, you take the oscillation time, which is given here, and you rearrange the equation to solve for the spring constant, which I found my spring constant to be 7.05 newtons per meter. And then we can calculate the relaxed length by using the relationship between the force of gravity and the force of the spring, which is essentially, you can isolate the relaxed length, which I found to be 0.1410 meters. These are the results that I got from my tracker analysis. As you can see, in both the X and Y direction, the spring moved in an oscillating pattern similar to a sine wave, which is shown here through the data. This is the beginning of the code where we initially set up all of our factors before beginning the experiment. So we put in the mass of the ball, which was 0.402 kilograms, and the initial position of the ball, which was given by our tracker data. Here we also have the gravity constant and the spring constant, which was calculated, and L0, which is the relaxed length of our spring. Following that, we have L, a variable which represents the vector L, the length and orientation of the spring, L hat, which is its orientation. Then we have S, which is essentially the displacement of the spring. Then next we calculate in the next section our kinetic energy, our potential energy of gravity, potential energy of the spring, and the total energy. Here we get into our calculation loop, which is while t is less than 9.307, which was the total time of our experiment, we define our initial energies by setting Ki, UGI, USI, and EI all to the current energy variables. We make a vector for gravity, a vector calculating the spring force, and then we calculate our net force. Then, of course, we go through the usual, calculating the velocity and position as it updates. And then we update the spring using the same equations that we used earlier. We align the spring's axis and we draw the trail. Next, this is still within our calculation loop. We are calculating the energies again and then calculating the changes in energy, which we'll plot on our graph, as you'll see shortly. Energy graph, the blue line representing the change in kinetic energy, the green line representing the change in the spring's potential energy, and the orange line representing the total change in energy, which is none, which aligns with our ideas regarding how the energy should change when the system is not giving energy to the surroundings. Next, you can see we have the change of position over time of our predicted model in blue and our actual observed model in red, which actually throughout the experiment they align pretty closely, so that suggests that many of our calculations were most likely correct. So final thoughts to close out is, does our model satisfy the energy principle? So as I stated earlier, as you can see, the total change in energy was 0 given by the orange line. And so essentially that suggests that this experiment does satisfy the energy principle. Lastly, we calculated the period, the data that I used the Y value, but also the X value presented a different value. So these slight differences will lead to a different calculated net force and different predicted motion as a result. Thank you for listening and have a great day.